Okay, we should be good now. Okay, so Sawyer, what did you find for gravity?
A force that attracts something or someone who's standing for it.
Good. So it's a force that attracts another object. Good. What? Anybody find anything else? What determines how strong gravity is? There are two things. Anybody? Mass is one, yes. And what? Not energy. Think. What would determine if I was playing with a magnet? What would determine of whether something's gonna actually like get sucked to the magnet? Where do I need to bring the magnet to get it like to finally pick something up? Distance. Right, distance. So mass and distance. Very good. So it's a force that I'm going to add with a mass. With mass that attracts another mass. Is also determined by distance. All right, so what this is saying is that anything with mass has a certain amount of gravity. Do we feel that gravity all the time? Like, do I feel the pen, the gravity of the pen that's really close to me? No. What is so much bigger that would really be affecting gravity here on Earth? What are we the most attracted to on Earth? The Earth itself. The Earth itself is huge compared to us or all the objects on the Earth. So we are being attracted, we are being pulled down to the Earth from its gravity a lot more than the gravity of this pen. So I don't feel that I'm being pulled to the pen, even though technically I am because it has mass. But the Earth has so much more mass, so if I drop my pen, where is it going to go? Earth. To the Earth, right, straight down. All right. All right, what formula did you guys find for gravity? I'm gonna look this one up online. I'm gonna pull this from the internet. Anyone? What do we find? Did we find a formula or an equation?
It's like F equals G and then a fraction M1, M2 at the bottom.
Good. All right. Because that has the division and the squared, I am going to pull it up from here and actually just copy it. Again, I want to find one. Gravity Falls formula. I want to find one that has all the descriptions of what's there. So I'm going to use this one here because it has everything labeled. So if you guys don't have, if you have just the formula, like what Maddie just said, then you want to make sure that it also has, the labels for everything. We are not going to actually use this formula, but we are going to be using gravity. So gravity is actually a constant when we're talking about the acceleration of any object to the Earth. Because the Earth's gravity doesn't change, it doesn't matter what it is that's falling to the Earth, it's going to fall at the exact same acceleration. Anybody find what that is? Or anybody know what the acceleration is due to gravity? All right, so this is a number you guys need to memorize. You will be using it. We're going to use it this year for the rest of our year, but you're also going to use it once you get to physics. You guys are going to use it a lot in physics. So it's one of those numbers you want to memorize. Some people will round it to the nearest 10 or whole number, but it is 9.8 meters per second squared. So we do want to have this in our formula. So what that's saying is Sorry, let's square this first. All right, so what's that saying is if something is falling to the earth, every second it's going to go an additional 9.8 meters per second. So for my picture, I'm going to find a picture of that so it makes it a little bit more clear. But what are some things that we would notice gravity having an effect on? Jill? Okay, so car going down a hill. Good, or anything going down a hill. Yep.
Apple falling from a tree.
Good. So thinking about Newton's discovery of gravity, apple falling from a tree. We have like a skydiver. Good. All right. So I'm gonna find gravity. All right. So for my picture, I'm gonna use this because it makes it a little bit more clear with what acceleration due to gravity is. So this guy's standing on top of a cliff. He lets go of a ball. In the first second, it accelerates 9.8 meters per second squared. So it goes from here to here. In the second, do we notice it doubles and then it triples and then quadruples? So for every second that goes by, it adds another 9.8 meters per second squared. Does that make sense? Yes? So we can see that every second it actually gets further and further and further apart. All right, so free fall would of course have to do with gravity again. What is the definition of free fall? Yep.
I said downward movement under the force of gravity only.
Perfect. Okay, so the downward movement under the force of gravity only. So like I demonstrated before, I picked up my pen, I let it go. Gravity pulled it down to fall onto my table. Did you guys find a formula for that one? What do you have?
It's like triangle y equals 1/2 d times t in seconds.
Okay. The triangle y, remember the triangle is the change. Hold on. I lost my cursor. I think I really just want you guys to have the acceleration due to gravity. So it would just be, this is what you found, right? Mm-hmm. Okay. Let's change, I'm trying to see if there's anything on here to change it to. We're going to change that equation. So whatever you guys found, we're just going to make it this one, acceleration due to gravity, because everything on Earth, now this is just talking about Earth. If we were at a different planet or in outer space, if I let something go in outer space, what would happen? It would just float. It would stay where I left it, right? Because there is no gravity. So we're going to use the 9.8 meters per second squared again. Because that's how we're going to that's how we're going to calculate anything that would be in free fall. All right, when is the time that something would be in free fall? Skydiving. Good. When else? Jillian?
I said dropping a ball down the hill.
Good. Dropping a ball down a hill. Okay, and then I'm going to do free fall. All right, so I'm going to use this picture right here because it gives us a couple of different ways that something could be in free fall. It doesn't have to be straight down, like if you're shooting a basketball, it could be curved. Once it reaches the top and gravity takes over, we can see that how it spreads out. This guy just threw it straight up and down, and then this guy just dropped it straight down. So an object can be in free fall whether it's in motion in one direction or if it's just being dropped straight down. All right, then we have something called terminal velocity. So terminal velocity goes along with the free fall and the gravity. What did we find for the definition for this? Terminal velocity. What's the definition of terminal velocity, guys? We're almost done. Let's finish this up. Go ahead, Maddie.
Maximum velocity attainable by an object that falls through liquid.
Maximum velocity. Say the rest of that.
Attained by an object that falls through liquid.
Okay, what is velocity again? So yes, that's a good definition. What is velocity again? Go back up to your definitions. What's the definition of velocity? Yep. Speed and direction. So it's the fastest an object can move where eventually it's not going to continue to accelerate, meaning it's not going to get any faster. It's going to continue going down at that speed, but there's a point where everything will reach a speed that it's not going to continue to increase the speed. And we're going to understand why because of our next definition. All right, so I'm going to use that definition, just kind of reword it a little bit. So let's go ahead and use our next vocab word. So when air resistance so it's the force going in the opposite direction of a free fall. And gravitational force are balanced. So remember we learned about balanced forces. So that means the gravitational force going down and the air resistance, which would be in the opposite direction going up, would then be equal to each other. Because the object's already in motion, it's going to continue in motion, but it's not going to be going any faster. Does that make sense to everybody? I'm just going to make another note. So acceleration no longer increases. All right, I'm going to see if I can find a picture for this one to explain, because again, balanced forces, it's just adding the two forces together. So let's see if I can find a picture. Okay, this will be a good one. So even though, again, remember balanced forces, it's just adding the forces together. So this is more of a visual to help you understand the equation. When, I don't even know what this is a picture of. Oh, this is a skydiver. So see, this is the head and those are the feet, and that's his little parachute thing. So when a skydiver is falling down initially, there's really no air resistance. There's nothing being pushed up against them. They're not building up the molecules underneath them to slow them down. And then as they drop, there's a little bit of force pushing up on them. And then as they continue to go down, there's more force pushing up on them to eventually getting to a point where they're not going to continue to go any faster. All right, so what are some examples? We have one right here. What example would this be? Skydiving again. So I'll use jumping from a plane. Is there any other times that we might experience terminal velocity? Anybody think of anything? Avery?
Falling off a cliff.
Okay, falling off a cliff. We include cliff jumping. And picture up. So there is an actual equation, but we're just gonna do the balanced force for the equation. There's a couple of pictures we could use. Now, terminal velocity does change based on how big the object is. And we're going to understand that a little bit more when we talk about air resistance. And then I'll go back to explaining terminal velocity a little more, just so that it makes a little bit more sense for your quiz or for your test when you guys are there. So what do we have for air resistance? What is the definition? Yep.
A type of friction between air and another material.
Perfect. So a type. Was friction one of the words we did? Was that a vocab word? Okay. So remember, friction is the force that goes in the opposite direction of motion. So a type of friction I'm going to include or fluid resistance, because remember we learned that air is a fluid. We did that when we did the whole paper airplane lesson that we worked on. So our fluid resistance going in the opposite direction of motion. Did anybody find an equation for this one? I don't really need you guys to have an equation for this. Did anybody find one? No? All right, so we don't need to know specifically the equation. We just need to know what it would be measured in. So what would air resistance, if it's a friction, which would be a force, what would it be measured in? Anybody? What are forces measured in? Yep.
Newton.
Yes, newtons. All right, what are some times you guys notice air resistance? Jillian? Okay, so the paper airplane. Yes, when we were throwing the airplane, some of them spun around, some of them did all weird, they didn't really fly right.
I said a parachute.
A parachute, good. Archer?
I just get drugged tonight.
Okay. It doesn't have to be just in a free fall. Are there other times that you guys have felt like air resistance? Come on, you guys feel it all the time. How many of you like to stick your hand out the window when you're driving? What does your hand do? You guys ever do this?
Yeah.
Where you like go up and down? I always thought that was fun when I was a kid. So what's happening is you have the air going on your hand, and then as you bring it up, it's like pushing your hand back, and then so you're trying to counter it to go straight again, and then it goes down and it pushes it down. So you have that air resistance when you're putting your hands out the window. What's another time? Yes, thank you. Yeah. Riding your bike. It doesn't even have to be upwind. If you're just riding your bike, you're going to feel the wind blowing in your face. Yep. Going on a roller coaster. Good. So air resistance doesn't have to do with free fall, but we're going to most likely be using it more with the free fall. All right, so now air resistance, when we're going back up to terminal velocity, will change based on how big an object is. So if we're jumping from an airplane, have you guys all seen a person, like a video of a person jumping from an airplane? What happens as soon as they open the parachute?
They slow down.
they slow down. It looks like, because usually it's somebody going down with them, it looks like they're actually going back up in the air again, which that's not really what happens. They're just slowing down. So yes, once the parachute opens, because it's bigger, it's able to kind of capture more molecules underneath it. So remember, air is made out of molecules. So because more molecules are bunching up underneath it, it slows it down to getting that terminal velocity. So the air resistance is what would save us from dying when you jump out of an airplane. Does that make sense for everybody? Anybody need me to explain that a little more? Avery?
I was going to ask if I could go to the bathroom.
Yes. We're close to being done, though. You sure you want to leave?
Yeah.
Let's see. I don't know what that picture is showing. Let's use this one here. Actually, this is a good one. All right, so we can see what's happening here. We see the molecules kind of bunching up underneath him, and that's what's going to be slowing him down. So I like this picture. All right, so remember last time, which is a couple of days ago now, we talked about using the right size letters, like capital letters versus lowercase letters, to represent words. So momentum is one of those ones I specifically talked about, where mass, meters, and momentum all use the letter M. Momentum is capital M, though, where mass and meters would be the lowercase m. So if you see a capital M, that means we're talking about momentum. What is the definition of momentum that we found? Anybody? Momentum? Yep.
Gaining of motion through moving objects.
Good. So gaining. What? Okay, for a moving object. So what would make it? What would affect the momentum? There's two things that affect momentum. Speed and think. If I throw a, yeah, not distance. If I throw, what were you going to say, Alex? Velocity and speed are the same thing. Remember, so speed in a given direction. And if, let's see, if I throw this pen and the stapler at Sawyer's head, both at the same time, which one is going to have more momentum? They're both going to have the same amount of speed. Yep.
Mass.
Right, mass. So this is what might hurt him, where the pen, maybe not. So what I usually use as an example, if you're standing in the middle of the road and somebody throws a tennis ball at you at 25 miles an hour and it hits you, you'll feel it, but it won't be that bad. But if a car is going 25 miles an hour, which really feels super slow when you're sitting in the car, but if that hits you, that could be really bad, right? So a car that has a huge mass would have a lot more momentum and cause a lot more damage. So due to its mass, and I'm going to use velocity instead of speed, but so the direction that it's going in. So what is the equation for momentum? Yep.
I got P equals mv.
Good. So P equals mv, where the P in this case would be momentum. The M is mass and V is velocity. All right, so in this case, we're not going to use the capital M for momentum. We're going to use the P because we already have the mass in the equation. All right, so we gave some examples already. A car versus a tennis ball going 25 miles per hour. They're going the same speed, the same direction, but one has more mass, so the car would have more momentum. What did you guys find for a picture? Let's use this one. So we have a bike going down a hill versus a truck going down a hill, and it's 4 kids standing in the middle of the road. So that'll kind of refresh your memory. All right, we are on the last two. So these are 2 types of energies that we're going to be going into as soon as you guys are done taking the test on the vocab. So we're going to learn a little bit more about this, but I'm pretty sure you have all heard about and learned about potential and kinetic energy, right? Yes, Archer.
Never mind.
Okay, if it comes back to you, let me know. All right, what's the definition of potential energy? It's energy that what? Yep.
All that is stored up over time.
Not over time. Stored up over time, is that what you said? Mm-hmm. Okay, I'm just going to say stored. Good. There's 2 kinds of potential energy. Did you guys find those 2 for the equations? When you found the equation for potential energy, what did you guys find? What's one? What equation did you guys find? Anyone? Yep, Jillian? Okay, so PE equals mgh. That's one. That's called gravitational. So gravitational potential energy would have to do with something's what?
Falling.
Something falling, right? So not actually falling because it would be stored. So how would I store the energy? Where would it be located? Right, like in the air, right? So it would have to do with an object's height. If the object is on the floor, does it have stored energy? No, it can't do anything. It's already on the floor, right? If an object is up over your head, it's stored energy, and you have to hope, like if I'm holding a bowling ball over your head, could it do work on your head if I let it go? Are you going to feel it? Yeah, it could do a lot of work, right? It could really hurt you.
And most likely kill you, it's probably, and if it didn't kill you, probably severe brain damage.
It depends on how high it is and how heavy it is, but yes, it would be very dangerous, right? It has the ability to do work. We could really see it if I let a bowling ball go over sand. Would it make a big dent in the sand? Yes. Before I let it go, though, the energy is stored. So it has the ability to do work and the potential to do work, but it's not actually doing anything. It's not doing any work. So the energy is stored in there. I put it in there as I lifted it up over the sand. All right. The other one, did anybody find a different equation other than PE equals mgh? Gravitational. Nobody found any other equations? I mean, I would assume, I guess, if you guys just found the one, then you figured that would be it. So we have this one here. What's another way we can store energy in an object? You guys find something else? Like, other than just lifting it up. Anybody do archery? Anybody ever try archery, even if you're not good? So what do you do before you actually shoot something?
You have to pull back like behind your ear then that has like enough potential energy so I go like there goes like.
Good. How many of you have a trampoline in your backyard?
I used to.
So when you jump down, eventually you'll spring back up, right? So that's another type of potential energy. Another one would be shooting like a rubber band.
Yeah.
Anybody know what this kind of potential energy would be? Rubber bands are what? They're very stretchy. So elastic, very good.
Yeah.
So this would have to do with like a stretch or compress. So either stretched or compressing something. So we have elastic potential energy. So they are two different types of potential energy. Do you guys understand the difference of the two? So their equations are going to be different because for the gravitational one, it's going to include gravity, the pull of gravity, which is 9.8 meters per second squared. So that's part of the equation. Where elastic potential energy, let's use this one because it tells us what it is. So this one would have to do with the spring, so the tension or how we're stretching or compressing it. This, if you ever have to do this formula, like the numbers would be given to you, so you don't have to calculate it, figure it out. It would always be given to you. All right, so what are some examples of potential energy? Yep.
I said a yo-yo.
Good, a yo-yo. What else? Anybody? Go ahead, keep going. A what? Bow and arrow.
And also it's coming in.
What? Oh, archer.
Yes.
I get it. Right.
and actually I have a bow and arrow in my house.
Do you? I have, my boys each have one too. All right, any other gravitational or elastic potential energy? I just gave you guys a bunch of examples. What else? Let me see it. Yep. A bowling ball, like being held up. We'll say over sands and not over somebody's head. A trampoline or jumping on your bed. A roller coaster. You guys ever notice with roller coasters, the very beginning, any big one, you hear that click, 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 and then you get the very top, and then you never hear that again. It's all because of your gravitational potential energy. We're getting to a certain point. They need to put a lot of energy into that. We get really high, and then the gravitational potential energy is what takes over, and that's what makes the roller coaster glide through the rest.
Oh, never mind.
Let's do a roller coaster. What were you gonna say, Archer?
Nothing.
So Miss Kinkella usually does in her class. She usually does roller coasters. They build a roller coaster and then they have to label all the parts of it using what's the potential energy or the greatest potential, the greatest kinetic energy. We are going to be doing similar. We're going to be making our Rube Goldberg, but we're also going to be labeling it with all of our energies as well. Here's a good loopy one. So you can see it starts off super high. Yep.
I'm not sure it'd be a pretty good one. Nitro.
Oh, nitro, yeah. I actually blacked out on nitro when it first opened. I was awake, but I couldn't see anymore. All right, so kinetic energy would be the opposite of potential energy. What would we use for a definition for this? Yep. Due to motion. So it is moving energy. So anything that's in motion has kinetic energy. And there is a formula for that one, so I'm going to find one that explains what all of the letters stand for. Good, we'll be able to start our escape room today. I get rid of roller coaster. All right, so I'm going to use this one because it tells us what the M, the V, and the kinetic energy, what all the letters stand for. This one, when students do equations, you always need to remember, and same thing with elastic potential energy, because we have something that's squared in there. You always need to remember to do PEMDAS. So you always do the exponent before you do the multiplication. That's where most students get the problems wrong. All right, so for this one, we have the velocity squared, but it's times mass. So what a lot of students would do is the one half times mass times velocity, and then square that number rather than squaring the velocity and then multiplying it by the 1/2 in the mass. Are you guys all familiar with that? Like, do we understand that? Okay. I will give you practice problems before you actually take a test on the math part of this. So right now, we're really just focusing on understanding what each vocab word stands for. All right, what are some examples of kinetic energy? Yep. A river flowing, okay. What else? Yep.
A ball rolling down the hill.
Good. So a ball rolling down a hill is a good example of actually it having some potential energy because it's still at a certain height, but that potential energy is slowly transforming into kinetic energy. So anytime we are talking about, or same thing with elastic potential energy or elastic potential and kinetic, it's usually transforming from one type of energy to another. I was way off of the sponge for this one. Rolling down a hill. Good, and then let's look for a good picture. Does this one say? Let me see what this says.
Potential.
I know it's potential here, but I think it says kinetic there, but it's too blurry. Potential again. I mean, everything has the potential energy in it before it has the kinetic energy. Okay, this one here. This says potential and then kinetic when it's in motion. So for this one, the ball isn't what has the energy. It's the guy's leg because he's stretching his leg. So anytime you move your body, you're stretching a certain muscle and contracting another one. So his hamstrings are bringing his leg up and he's stretching his quad. So the further he brings his leg back, the more stretch it has, which means the further the ball will go when he releases it. Same thing, have you guys ever tried to jump without bending your knees? it is super hard and you go like nowhere, right? But once you bend your knees down and try to jump up, you'll be able to go a whole lot higher. It's because you're adding that stretch into your muscles. You're stretching your muscles, and then when you jump up, you're making them go back to their normal size. Yeah, you're not going to get very far. But now try to bend your knees and jump high. Right, a whole lot higher, right?
It's very hard.
All right. All right, going back through all the vocab words, does anybody have any questions at all about any of them? Anybody need clarification? We're all good? Okay, so what I'm going to do now is try to stop the recording. I'm going to put the escape room. I just have to remember how I did it. Yep. Yes. I think it was a Google form. Yep. Yes. All right, let me just find the escape room really quick that I want you guys to do. If you want to work with somebody, you guys can partner up. Just make sure I don't want it bigger than 2 people, because once we start getting more than that, some people stop participating and let other people do the work. And we're not trying to do the work, we're trying to practice, okay? So I'd rather you not partner up with more than 1 person. Force and motion. Sorry, the computer is just moving really